So I'll go back to today's topic directly. So if you have any question in the middle of class, just stop me. Otherwise, I'll be faster and faster. So it is you who have to stop me. This is a class note that I used while I was studying at United States. So it is called continuous time finance. And again, you can download this PDF file in our syllabus, in our class content. So first type is martingale. What is martingale? Martingale is a stochastic process. Stochastic process is basically a collection of and then we index those random variables with time. You don't have to write down anything, okay? So suppose you don't know what is stochastic, you have a question about what is stochastic process, you don't have to write down, just Google it. Stochastic process. Everything is on the web, so what's the point of writing down? Stochastic process in probability theory. Stochastic process or sometimes random process is a collection of random variables. Okay, same. Represent the evolution of some system of random variable over time. It means that it is a collection of random variable and we put names for each variable. Like we give index with time. So like x1, x2, x3, something like that. This is so stock price is stochastic process. We can observe stock price every day. So it is naturally indexed with time. And tomorrow we don't know what is going to be about stock price. So there is a randomness in the stock price. So it is stochastic process. If you draw coins, it will be either head or tail. Right? So it is a series of, if you throw coin multiple times, it will be like head, tail, something like that. That series is random variable, stochastic process. If we put index for each trial, first trial, second trial, third trial, something like that. One problem of Wikipedia is it has just too many explanations. Right? Anyway, so that is stochastic process. So martingale is a subset of stochastic process. And the definition of martingale is those two. If a stochastic process satisfies these two properties, then it is called martingale. Property 1. For each random variable, for each one, the absolute expectation, mean or expectation of the absolute value of each random variable is less than infinity. Of course, it should be greater than 0, right? Greater than 0, because it's absolute value. And if it is less than infinity, we call it is well defined. So first property is martingale should be well-defined stochastic process. Second one is more important. So conditional on previous trials. Okay, so again, this index is time. Conditional on previous trials. Your expectation on the next trial is just the most recent value. So if stock price is martingale, what would be the best prediction for tomorrow's stock price? I'm asking. If stock price is martingale, what would be your expectation of about tomorrow's stock price? 네? 이거 뭐라고 한 건데? Yes, it should be today's stock price, right? Anyway, martingale is related with efficient market hypothesis. I will discuss that later. So any question about martingale? It's straightforward, right? Very easy, well defined. Expectation for next period is just the most recent information. The most recent value is just your prediction. And actually we can slightly generalize martingale. Okay, let xn, again xn is random variable and we give index with time. So again, this is a stochastic process, and then we have another stochastic process yn, and then they are stochastic process, and we can say xn is a martingale. Okay, now the wrt is with respect to yn. If it satisfies these following two properties, it is very similar. First, the stochastic process xn is well defined. Second, given the information of yn up to time n, your prediction about the next x is just most recent value of x. So again, if x is stock price, and then y is the information you have. As time goes by, suppose you don't forget anything. As time goes by, you have more and more information. Right? So y is kind of information set. So given the information up to time n, okay, prediction for the stock price for next period, xn plus is just most recent stock price. Right? So this is slight generalization of the previous one, because y0 to yn can be x0 to xn. So that is the special case of this one. It is useful to think of y0 to yn as the information or history of the time or stage n. As I told you, so from y0 to yn is history, just information up to time n or stage n, whatever. And naturally, it is given the information up to time, it is a prediction about the next period x. And martingale says that it is just most recent. Again, if you are more curious about martingale, you can of course Google it. Martingale again, probability theory. You can read this one. Okay? They have maybe too many details, but you can understand. You don't have to read solve martingales, super martingales. You can read only up to this part. If you have a question. Martingale representation theorem, martingale, yeah. So it is okay, right? Okay now. It's all bunch of definitions. Until now, there is no calculus error. So the history determines xn, right? In the sense that xn is the function of y0 to yn, right? So history determines xn in some sense, because this is a conditional expectation, right? Everyone knows conditional expectation, right? I think it is in the high school textbook, at least. 조건 확률 배웠지 고등학교 때. So it is conditional expectation. Conditional information y0 to yn. So this is constant. So this conditional and this information we formate. Okay, we form our expectation about xn plus 1. So basically, this entire thing is a function of y0 to yn, right? So you can regard it as a function of y0 to yn. So xn is in that sense a function of information from y0 to yn. xn is a function of history of yn. Okay? Therefore, we can say that the history determines xn in the sense that xn is a function of y0 to yn, i.e., knowledge of the value of the y0 to yn determines the value of yn, but no, value of xn, but xn plus 1, right? It is just restatement of this definition, and it is just the definition of conditional expectation. Conditional expectation is function of those conditioning informations. 뭐 질문 있어요? 질문이 한국 학생들 질문 있으면 한국어로 해도 돼요. This is English only class, but if you have a question can be asked with any language as far as I can understand. 예, 조연정. 네. So about our first condition, okay? Okay, that's a good question. If it is infinity, we cannot define this one. If it is infinity, then there is no expectation. So we cannot define this one. That's the whole point of this. Yes. So if this is infinity, then we say expectation is not defined. There is no, actually in that sense, we say there is no expectation. Mean does not exist. Since mean does not exist, we cannot say this one. It's just a technical. If you learn mathematics, there is always those technical conditions. They are mostly not that important unless you are to write dissertation or academic articles with mathematics. They are usually not important. And whatever in your career, I'm pretty sure that you'll never see any stochastic process that violate this condition. So don't worry about it. Any other question? By the way, this class note, this PDF file was a class note that I used, that I learned. Actually, I learned continuous time in United States, and this was the class note used by the professor at the time. Okay, and then sometimes you can see small. Small writing, something like this. This is actually my writing. During the class, I wrote down this also. And this class note was written by very famous professors. So it has Hui Yang and also his professor Hua He. So this looks maybe horrible with not a pretty calligraphy. Okay, but still it is written by a very famous professor and it has some authority, I think. So xn from x0, xn is xn, okay? Right? It should hold, right? So when we have x plus 1, it's xn, but xn is, if we have information from y0 to yn, then we have already information of xn. So xn is in some sense just constant. So expectation of constant is just constant. So if it is n or like n minus 1, it should be n minus 1, something like that. Right? Because we already know that value. It is in the history of our information. So actually it is some meaning is to take expectation. Of course we can prove it by mathematics using the law of iterative expectation. I'll explain to you. Okay? Expectation of xn plus 1. Okay? Expectation of xn plus 1 is, we can write this as expectation of xn plus 1 and then some information up to time. Therefore, we say that expectation of xn plus 1 is same to expectation of xn. Okay? So this is the same to this one. Okay? So this one, let's look at this one carefully. Indeed, this one is not conditional expectation, right? It is called unconditional expectation. So for this one says that for unconditional expectation, for martingale process, on the value of unconditional expectation is same to everything. Right? And this property is called law of iterative expectation. And if we use more general notation, it is actually law of iterative expectation. Okay? So actually, there is a typo. This big G is just a small g. This G, this G, this G should be all same. A typo. Suppose G is a subset of H. Okay? Then conditional information G. So if we regard G and H as information, and G set of H is that H is bigger information and G is small information, right? So suppose we take expectation about set G and we want to get the conditional expectation of X. Then it is same to, first we take expectation, this is, to make it better, we have to actually put another expectation over here. Okay, H. Law of iterative expectation means X. G is, first we take expectation with H. So first we take expectation of X with more information. Okay? And then we take another expectation with G. Actually, so this is a shorthand notation of this one. And so it looks somewhat strange, but it is actually very intuitive. You can prove it mathematically, but actually mathematics is not necessary to prove this one. It is very intuitive one. So H is bigger information than G, right? So let's say G is information up to today. Okay? And H is bigger information, so let's say H is information up to tomorrow. Okay, something like that. So then, if we assume that you don't forget anything, okay, information up to tomorrow should be larger than information of today, right? Right? And let's say X is like stock price 1 year later, something like that. Right? Some stock price of the future, more than tomorrow or the day after tomorrow or 1 year later. Then it says that, okay, let's figure out what would be stock price 1 year later given the information today. Okay? This is what said. That's usually what stock analysts do, right? Given the information up to today, I want to know what would be my expectation of stock price for the some time. Okay? This should be same to conditional on information. So we have a time capsule. So let's assume we are tomorrow. Tomorrow we will have new information, right? So tomorrow we can form expectation of a stock price. Okay. Of course, tomorrow, since we have more information, this one is different. Okay. So tomorrow we have some of this one. Okay. But still we are in the today, right? Because there is no time machine, right? Available. This technology. So since we are today, so we have to take this one now, expected again with today's information, and then take expectation again, right? Then because we are still today, okay, information tomorrow is not available anymore. So if we take conditional information 2 times, then we have only information for today, right? Because we are still at today, right? Therefore, this one class 2, so this one should be same to this one. So taking expectation with information today should be same to the expectation value that suppose we are at tomorrow and take expectation again, and then that we take expectation of that expectation given today, and they should be logically should be same, right? Again, if you have any question, you can type Google law of iterative expectation. This is actually very important in finance. Iterative expectation. Law of total expectation is another way of law of iterative expectation, or someone says it's a tower property. In mathematics, it's called tower property. Oh, there is even YouTube about iterative expectation. Right? And there is better English, better explanation, and so.
음에 지금 그게 뭐다요? 아이 차례상엔 홍어죠. 아이고 참나.
어머니, 그래도 술은 백화수복 맞죠?
그러지.
대한민국 어디서나 재래주는 백화수복.
You know, internet is amazing. There is even lectures about iterative.
Another thing I'd like to show in this video is something called the law.
So Wikipedia law, the proposition in the probability theory known as law of total expectation, or law of iterative expectation, or law of iterative expectation, or the power, the smoothing theorem, Adam's law. They are all same thing. Okay. Among other names, states that if x is an integrable random variable, it is technical condition. It is almost same to absolute value is less than infinity. Okay. When it satisfies some technical condition, then y is random variable, not necessarily integrable on the same probability space, and expectation x is conditional information of conditional information. I.e., the expected value of a conditional expected value of x given y is the same as the expected value of x. Okay, you can again prove it mathematical, but it is almost a logical statement. One special case is that if it's a partition of the whole outcome space, then something like this. Proof in discrete. There is even proof. Very simple. This one is if it is discrete space. First, this part is conditional on y. So by the definition of a conditional expectation for conditional on y, we can get the expectation of x. So it's a definition of expectation in the discrete space. 이산 확률 분포, okay? It's a definition of expectation in the discrete space. And then, again, there is another expectation. So by the definition of expectation, again, if we apply the definition of expectation again, then because we have y, so each state of y, we have y, this one. And we can summation of a summation, where we can combine it, and summation of y for each state of y, for each state of x, we condition x and probability x given y and probability y given small y. Okay, and then if we calculate the x is just constant for each x, so actually we can, because of this summation, okay, we can change the order of summation first. Okay. We can change the order of summation first. If we change the order of summation, then for y-x is a constant, so we can put constant in front of it. So summation of x, y, and this one. Then we can say it is just what? For each y, for each x, for all state y. So it is actually this is just this part. This part is just the just 교집합. Well, how can I say it? It's a joint definition of joint probability, right? So this conditional probability multiplied by probability is joint probability of x and y for joint probability, and we sum all y, and for some y then it is just x, right? And so it is definition of ex. And proof in general case it looks horrible, so yeah. If you are interested you can read this, right? But anyway, this is mathematics is simple for both discrete, and this is looks horrible, but it is very simple statement anyway. So mathematics is simple, but still I think important thing is you have to understand this law of iterative expectation logically. Okay, logical understanding is more important than this bunch of equations. 질문 없나요? Do you have any question about law of iterative expectation? So when we have nothing here, okay? 내 수업이 싫어서 벌써 떠나는 건가? yeah. Anyway, if we have this relationship, this is, you know, empty set is subset of every set, right? And then we sometimes write, right? We can write this one. Expectation without any information is called unconditional expectation, and the shorthand notation of this one. Okay, because it is unconditional, because we don't have any information, so it is unconditional expectation. It's usual expectation we know. 그냥 expectation, 그렇죠? 조건부 기대값이 아니라 그냥 기대값이. Conditional. So unconditional information is conditional information trivially on the conditional on empty set. Right, so this expectation of xn plus 1, it is, we can say that it is a conditional information on empty set, right? Empty set. And then if we apply law of iterative expectation, then let's say e xn plus n give some information and conditional on empty set, right? And then if we use law of iterative expectation, and by the definition of Martingale, this part is simply xn, and expectation of xn conditional on empty set is just expectation of exn, right? Very simple. Therefore, if you have a Martingale process, unconditional expectation or conditional expectation, conditional on empty set is the same for everything. And in finance, we usually assume that stock price follows Martingale process in very short time. Of course, in the long run, like 1 year, then we know stock price usually go up. But in the very short, like from today to tomorrow, we assume it is almost Martingale. With the intraday stock price, we usually assume it follows Martingale process. Because in daily, stock return would be very small in expectation. It is statistically not different from zero. 내가 3시간 연강만 하다가 이렇게 2개씩 나눠서 하는 건 처음인데, 이건 10시 15분까지 끝내면 되는 거지. 네, 그렇죠? So, example, okay? Example of the Martingale. Sum of independent random variables. Sum of independent random variables is Martingale. 잠깐만. 이게 이거 안 켜져. Sorry, I have to make sure that this class is correctly recorded. I have to check machines. I think it is fine. Okay, example. Example of martingale, sums of the independent random variable. Let y0 is 0. Okay. So starting value is 0. And y1, y2 are all independent random variables. So what does it mean by independent? 독립. Okay? If two random variables are independent, what does that mean? 독립이 무슨 말? 확률 독립. Wrong. That's definitely wrong. Okay? What does it mean by independent? Two random variables are independent. What does that mean? 이것도 고등학교 국어에서 나오잖아. 생각 안 나나? Where are you from? Germany. Okay. What is the German answer about the stochastic independence?
I would say so they're not dependent on another factor that we can foresee. So it's completely random. We don't see any process.
Okay, it is approximate answer. How about where are you from? Oh, okay. So it is BMW answer or Mercedes Benz answer. Okay. What is that? Yes, that is the intuitive definition. Where are you from? You are also from Sweden. Okay. Sweden, Volvo was Sweden, but it is acquired by a Chinese firm, right? Anyway. Yeah. Independence is actually a very important concept in statistics. Let's check it. Independence in probability theory. In probability theory, to say that two events are independent, alternatively called statistically independent, stochastically independent. Same means that the occurrence of one event does not affect the probability of other event. Okay? Similarly, this is actually more relevant definition. Similarly, two random variables are independent if the realization of one does not affect probability distribution of another. So if you draw dice, if I throw dice and if I throw coin, and they are, if I throw usual dice and usual coin, those two are should be independent. It means that whether there is tail or head occurred in the coin, it should not affect which number realized in my dice, right? So the number that occurring in the dice and the head or tail in the coin, those two stochastic processes are independent of each other. It means that conditional on the realization of the coin, whether I conditional or not, the realization with the coin, the realization of the dice should not be affected. So mathematical definition is this one. The intersection of A, B is PA, PB. And actually my preferred definition of actually this one, A. So this is my preferred definition. So A and B are independent of each other if it satisfies this. It means that probability of A should not be affected by realization of B. Okay? Whether we conditional on B or not, A is not affected. Whether we conditional on the realization of coin or not, the realization of dice should not be affected. Same. Realization of the coin should not be affected by one number happens in the dice. Anyway, it is okay. But I want to check who are in my class. So let me check the roll sheet. 서재민. 서재민. 오케이. 출석. 변경 사유? I think it's very stupid. So it means that default is missing. 이게 불출석이 디폴트네. 출석으로 바꾸면 변경 사유를 입력해야 되네. 말이 안 돼요. 그렇지? Anyway, let's try. 출석. 이태훈. 이태훈 안 왔고. 김서인. 김서인 3학년. 오케이. 그다음에 김세형. 김세형도 경영학과 3학년. 이 경영학과 3학년이 내 과목 들으면 전공으로 인정이 되나? 그럼 왜 듣지? 모르고 일단 그거 드롭할 건가? 그 방법이 있을 거야. 그럼 파이낸스 경영학과를 다중전공이나 뭐 부전공으로 신청하면 되는 거 아니야? 네? 파이낸스 경영학과를 다중전공으로 신청하면 어차피 과목이 다 겹치니까 어차피 다중전공 쉽게 되는 거 아닌가? 나 잘 몰라서 그러는데 안 그런가? 아니 그래도 경영학과 과목이랑 파이낸스 경영학 다 똑같으니 어차피 이제까지 들었던 게 으로 인정되는 거 아니야 어차피? 내가 알기로 그렇거든. 아 그래? 그렇구만. 너 두 사람은 다음 주에 안 오겠네. 그래. 어쨌든 예. 다음 이름 좋으시네. 김영삼 안 나왔어. 오 경영학과 학생들이 많구나. 유덕현. 유덕현 학생들 경영학과네. 경영학과 3학년. 아 여기는 파이낸스 경영학과구나. 근데 파이낸스 경영학과는 왜 이렇게 내 수업을 또 안 들어? 그런가? 주재호 파이낸스 경영학과 3학년. 그래도 파이낸스 경영학과는 재무관련 과목 많이 들었으니까 미적분은 잘 하겠네. 그렇지? 미적분도 하고 막 이런 것도 다 할 거 아니야. 통계학 수준하고 하겠지. 그런 거 없이 파이낸스 수업을 들으려면 상당히 힘들었을 텐데. 너 미적분 없이 예를 들어 듀레이션 이런 거 다 미분이잖아. 듀레이션, 컨베크티 이런 거 미분 적분 없이 배울 수 있는. 그냥 이해가. 이희윤. 네, 도고 동문학과. 파이낸스 경영학과 다중전공이에요? 다중전공하면 몇 과목이나 들어야 돼요? 45학점. 꽤 많이 들어야 되네. 15과목을 들어야 되네. 15과목 중에 또 의무적으로 들어야 되는 게 인사조직 마케팅 이런 것도 의무적으로 들어야 되지. 재밌어요? 파이낸스 다중전공하니까? 무슨 과목이 무슨 과목 들었어요 지금까지? 네. 네. 아주 좋은 과목들 다 들었네요. 계량 경영 들었으면 이거 다 무슨 말인지 알겠네. 아마 당연히 까먹지. 네. 뭐 당연히 까먹겠지만 그래도 한 번 까먹어도 한 번도 안 듣고 까먹는 거, 한 번도 안 듣고 아예 모르는 것과 배우고 까먹는 것과는 충분히 차이가 있지. 다시 할 때. 아무튼 파이낸스 경영학과 부전공에서 다중전공하고 부전공 차이가 뭐지? 내가 잘 모르겠는데 어쨌든 다중전공하고 아주 좋은 선택인 것 같아요. 독일어도 잘 하겠네. 그래요? 다음에 김밀영 학생은 파이낸스 경영학과 3학년. 근데 왜 지금까지 한 번도 못 본 것 같아? 파이낸스 경영학과. 네. 내가 며칠 전에 조교한테 한양대 위안이라는 사이트가 있더라고. 그렇지? 위안이라는 사이트가 있는데 거기에 막 교수님들 여기 많이 올라온대. 네, 그래서 Sorry, I'm speaking in Korean. It is not related to class content. It is just casual talk. Sorry. 예. 그래서 막 여기 많이 올라왔는데 그래서 이제 조교 보고 가입을 하라 그랬지. 네, 저기 이원이한테 가입을 해서 내 여기 있나 확인해 봐라 했더니 뭐가 많더라고. 네. 뭐 강의가 뭐 호러블 하다느니 뭐 아마 그것 때문이 아닌가. 네. 그래가지고 이제 조교 보고 뭐 체크해 말했더니 교수님 뭐 너무 오래 보지 말라고 나한테 못 보게 하더라고 자꾸. 어쨌든 그러고 있어요. 뭐 뻔하지 뭐. 네. 학생들이 뭐 할 일 없으면 뒤에서 교수들 욕하고 이런 건 뭐. 고등학교 때 담임 선생님 흉보고, 대학교 때 교수들 흉보고, 취직하면 직장 상사 흉보고, 뭐 다 당연한 거 아니겠어요? 다음 김범현 경영학부 4학년. 김범현 안 나왔나? 이한솔 나왔고. 네. 그다음에 조현정. 불편한 거야. 그다음에 허지원. 허지원 학생도 파이낸스 경영학과네. 2학년이네. 이 저학년 때 좀 어려운 과목 듣고 이런 게 좋아요, 사실. 아주 좋은 선택이야. 다음 최형석. 나왔고. Now, Klaus Robin Klaus. Okay, so you are economics student. Okay, you majored economics. So which city are you from? Sorry, I never heard of it. So are you happy that German national team win World Cup? German national soccer team won World Cup, right? So, yeah. Yes, you are happy, right? Of course. Yeah. And then Viquez Bormeo Felix Gustavo. Yeah. Where are you from? Mexico. Oh, okay. You know, Korean national soccer team and Mexico national soccer team met each other many times in World Cup, and Korean team always lost. It does not mean that I have a bad feeling about you, so don't worry. Yes, I remember. Yeah, semi-final. But I'm happy because it was so unexpectedly good performance for national Korean soccer team. So, yeah, that's fine. Losing to German at semi-final is perfectly okay. Yeah. And then Jason Pinedo. No. And Johnson. Yeah, so you are from Sweden. Which city of Sweden are you? Stockholm. Yes, I've been there one time. Yeah. I went there during the summer, and I was hanging around in the city, and I was somehow tired, and I saw my watch, and it is like 10 p.m. because still sun is there, so I lost track of the time. Because I never, usually in Korea when it is 7 p.m. it is dark, but in Sweden even 10 p.m. it was so bright. Yeah, in summer, so yeah. And then Lim Keren, Müller. Oh, you are okay. Nicholas Müller. Müller is the last name. Okay. So you are exchange students? Okay. So when will you go back to Germany? January. So what have you done in Seoul? Another eating? Oh, really? Okay. So what was the most fun place in Seoul? Yeah.
I was at a very good barbecue place at Wangsimni.
왕십리.
They have a tree inside, and then you have your own grill,
Okay.
and you grill a lot, and you drink soda. That was very good.
Yeah, that was very good. But that is also one of the most common restaurant in Seoul. And I don't think there is a good barbecue place in Hwangshimi. So if you do, ladies, please let them know the really good barbecue place. I cannot believe there is a good barbecue place in Hwangshimi. So okay, this is just the beginning. There are better and better places out there, outside of Seoul, in Gangnam or in Hongdae, Sinchon area. There are more better places, more fun places out there. So. And Jansun, Ellen, how can I call you? Maria or? Ellen, okay. So you are also exchange students. When will you go back to Sweden? December. Okay, so this is your again last. So usually you exchange students stay 1 year or 1 semester? 1 semester. So when did you arrive at Seoul? 1 week ago. Ah, I see. So what is your plan for the next 6 months? Not 6 months, but next. Study hard. You know, you can study hard in Sweden. So, I mean, of course, you have to study, but you know, you are in Korea, in Seoul, so I think exploring Seoul is also kind of study, and that's the point of you are here, right? So, please, Korean students, please help her to enjoy her stay in Seoul. Seoul is also a dynamic place like Stockholm. There are a lot of things to do, so please enjoy your time. And then Tola, no, and Stanislas, no, and Jiku, no. They are finance 경영 person. Okay, good. And save. Cannot read properly. No, again, this topic. So examples of martingale. Sum of independent random variables. So now you know what we mean by independent random variable. So let x0 is 0 and x1, x2, they are all independent random variable. And then technical condition. Expectation of absolute value of each one is less than infinity. And the expectation of each one is 0 for all n. And let's say x0 is 0, okay, static value 0. And we define xn iteratively, okay. The xn is the sum of y from 1 to n. Okay. So xn is a sum of independent random variable. Then this xn is martingale with respect to y. Okay, this is a typo. No 0. So sum of y is martingale with respect to y. Okay. Is it intuitive? It should be very intuitive in some sense. Let's take a look at it. It is easy to prove mathematically. We check the first technical condition first. We have to check technical condition first that it is indeed expectation of xn. Absolute value of xn is less than infinity. Expectation of absolute value of xn is expectation, by definition, expectation of sum of y1 to yn. Okay? And then it should be less than some absolute value of sum is smaller than sum of absolute values, right? Therefore, it is less than equal to this one. And we know each one is less than infinity. Therefore, sum should be less than infinity. So done. It satisfies technical condition. Now step 2. Now we have to really check the martingale, whether it's martingale. So to check martingale, let's form the expectation about xn plus 1 conditional on the history of y up to n. Right? So conditional expectation xn plus 1 on the history of y. And then by definition, xn plus 1 is xn plus the last one more piece of y. xn plus 1 is xn plus y n plus 1. Right? And the expectation is linear operator. It means expectation is linear operator. It means the expectation of x plus y is expectation of x plus expectation of y. It's a linear. Okay? The expectation of ax, a expectation. So it means a linear operator. 선형함수. So expectation is 선형함수. Expectation linear operator. So because the expectation is linear operator, we can separate out this part, right? We can calculate separately expectation of xn conditional of history of y. And then given this history, we already know xn. xn is already in the history. So this is simply xn. And next, conditional expected yn plus 1 conditional of history. Well, we don't know this one yet because it is not in our history, but in our assumption, right? This is 0, right? Expectation of n is 0. So this part is no. Okay, instead of stepping here, right here, let's take this one. Okay, let's take a look at this one and this one. Why this one and this one is the same? Why? Why is that? Okay, what I'm arguing is that, okay, now this one is simply xn is in the history of y, so it is we know it is already known value, so xn, so it is constant. Since you already know it is constant, expectation of constant is that constant. And about this part, this one and this one is same, and this one is assumption 0, so this is same to xn, therefore this one is same to xn, so it is martingale. Conditional of information xn, conditional expectation of xn plus 1, conditional of history n is same to xn, so by definition x is martingale. But the question is the last part. Why this one and this one is same? Why? 왜 같아 이거? Why they are same? Yeah. Yes, exactly. Yes, exactly. Yes, they are, by assumption, I said that y1 to yn is independent random variable. So event yn plus 1 should be independent of whatever happens in the history. Okay, so it is irrelevant. So same, 0. So it's martingale. So sum of independent random variable martingale. Next one, the variance of a sum is variance of a sum as a martingale. Okay, sum of a variance and with small adjustment, it is also martingale actually. Okay, let's find y0 and y0 is 0, and y1 to yn, they are all again independent. Now we have one more condition. Independent, not only independent, they are also identical. So they are identical random variable. Identical means it is if we throw dice, we keep throw dice. we don't change it suddenly. We don't suddenly change it into coin, something like that. Okay? So they are identical. Identical distribution. So they are identical. So and identical, and the expected value is 0. And because they are identical, their variance is all same. You know, it is a mean is 0, so the expectation square is just variance. So they are identical, so variance is all same. And let's define x0 as is 0 and xn is sum of the minus variance. Okay? And I want to argue that this is also martingale. Okay, we can check. Again, we can check the technical condition. First, absolute value of xn is simply this one, so absolute value of this one, and then we can separate this part and this part. So expected absolute value of this one plus this one. So because we put absolute value of this one plus this one, so actually this should be greater than this one, right? And then we have to show that this is less than infinity. And then thing is that in this case, this one is okay. Expectation of summation of yk square. Okay. Usually we cannot do that. Okay. So this one is moving to 0. So it is a it is sum of squares, right? And it is a squared sum. They are usually different, but in this case they are same because they are independent. All y are independent of each other, right? So the sum of square, it means that there should be a bunch of cross terms, right? Like what this is saying is that expectation of a plus b square is expectation of a square plus b square, right? Usually we cannot say that, but if a and b are independent of each other, because a plus b square is a squared plus 2ab plus b square, and the expectation of this cross term is 0 because they are independent of each other, right? Or because independent, we can put this one inside of this one because all cross terms goes away. Okay? And then this one is okay. This one is, if we divide this one with n, it is just variance, and if we multiply n, it is variance. So you have 2n sigma square, which is less than infinity. So it satisfies technical condition. About second condition, okay, xn plus 1 conditional on the history now, and then definition of xn plus 1 is y. Okay, so basically they are separating it. We separate it, so it is from k to n plus 1, but n plus 1 we write down separately. Okay. Xn plus 1 is anyway yn plus 1 plus k1 to n yk square minus n plus 1 sigma square. This is conditioning information. Okay. And then we solve out this one. We solve out this one, then it is just this one, right? A plus b square. So if we calculate this part, then yn plus 1 square 2yn plus 1, and this is some part, and plus this sum square, minus n plus 1 square, right? And then now we have plus, plus, minus, right? And then because expectation of linear operator can all separate out, okay? If we separate out, okay, first part, y and expectation of yn plus 1 square, condition of n, because they are all independently identically distributed. First, they are all independent, so we can get rid of this part. Realization of yn plus 1 is not affected by history of yn because independent, so we get rid of this one. And unconditional expectation of yn plus 1 square is by the assumption sigma square because they are identical. And the second part, expectation of this cross term. Okay, first this part is the sum of y from 1 to n. And that is in the that part is already in the history of my information. So this is basically constant. So if it's constant, we can plug out of the expectation because it's constant. It's in the history. And then expectation yn plus 1 conditional of y xn. Because again, they are independent, so I can get rid of this one, and expectation y is 0 by the assumption. So this is conveniently. Right? And then, yeah, write this. Sigma square minus minus last sequence is minus n 1 sigma square, right? Minus n 1 sigma square, but I think there's some in the law, but this is sigma square and this is minus 1 sigma square, so this cancels out. Actually, there's some typo. Yeah. There is the x because I am forgetting the test. Oh, this last part. This last part is this last part minus n sigma square. There is a jump. This one as this one together is xn, right? And then plus 1, so this is minus squares, and then we cancel this one out. This is 0, so it is empty xn. So conditional expectation of xn plus 1 given the history of y is xn, so it is martingale. Right? So there is a small jump from this line to this line because in the rest part, I have a square of this one, and I'm applying this one, right? Square of this one minus n sigma square, two parts together is xn. And conditional of xn, conditional expectation of xn, history of yn is in the history, so xn put out as a constant. So it is xn. So careful, there is small jump from this line to this line. You can also solve it out. Small jump is this part and minus n sigma square xn and expectation of xn conditional on yn is xn. Okay, so xn here. So there are two-step jump. Any question? 질문 있어요? 없죠? Okay, I think this is enough for today. And see you on Friday. 네, 금요일 날 발표 준비 해오세요. 잘 해오세요. Okay. For student presentation, yes, we will present this one. And one good news is that if you go to our course web page, and then there are slides, if you go to this slide, actually PPT slide for this one is already here in this link. So you can recycle these PPT files for student for class presentation. 이제 설명해 주면 되지. 설명해 주고 질문 받고 그러면 돼요. So any other? Yeah. Yeah, 한양 portal. Yeah. Another idea is you can simply type my name in Google. This is my name. Okay. If you type Google, then somehow because my name is not that common, so in some sense unique in English. So it is in the front so here, and then teaching computational finance. Another one is of course you can go 한양 portal, log in, go to class web page, and there is also link. Another question.
Is it correct that only term paper will determine your grade level for our course?
Yeah. So yes, for things that